Hello and welcome to El Zoominario. Today we have Nayomi Plaza Rodriguez. She's going to be talking about elucidating the nanoscale interactions between wood and water. Nayomi was born and raised in Mayaguez, Puerto Rico, where she pursued a bachelor's in mechanical engineering. Her undergraduate research experience inspired her to pursue a PhD in material science at the University of Wisconsin-Madison. Now, Nayomi is materials research engineering at the Forest Product Laboratory. Thank you so much, Nayomi, for joining us today.
Thank you for the introduction, Claudia. And thank you all for tuning in for my talk today. Before I begin, I would like to acknowledge my wonderful colleagues and collaborators here at the Forest Products Lab, as well as the Oak Ridge National Lab, as well as, the University of Wisconsin-Madison. So in my research, I am interested in my research, I'm interested in understanding what happens to wood as it absorbs water across several length scales. And today my talk is going to focus about the nanoscale regime. So what happens at the microfibril level as the water enters the wood cell wall and starts swelling the cellulose microfibrils? So why study this nanoscale with water interactions? Well, the forest products industry, it's already has a significant manufacturing GDP. But as we are having an increased global interest towards moving into more sustainable practices, we are revisiting wood and lignocellulosics as a material and looking at a lot of different new applications, from green electronics and solar cells, all the way to more sustainable building practices. And I have a couple of different examples here, from research as well as from the applied world. There's, for instance, this 25-story mass timber building built in Milwaukee, and it's going to be one of the largest mass timber buildings. So this is really exciting, of course, but because these materials are natural and hygroscopic, moisture content in them can impact processing properties and ultimately the performance, meaning that if we understand better how wood-water interactions occur, then we can come up with treatments that make these products more durable and really unlock their potential. And here I have a couple of examples of what happens, for instance, in building materials. When we have too much water in them, we can have early biodegradation, so it can decay. And if you have a deck and that was not properly treated before it was installed outside, you've probably seen some of these effects. Or you can have corrosion and those fasteners that are embedded in the wood. Or if you have a composite, it can start delaminating, so separating those spaces near the glue line when you get too much water in there. So let's talk about wood structure and why is it so complex, and why is it that I study it across several length scales. So it's a complex material, has multiple levels of structure, and at the macro level, it's anisotropic, meaning that its properties will change depending on the direction. And if we start zooming in at the sub-millimeter scale, we have a cellular material, and it has different types of cells along the radial and tangential directions. And this is just because Mother Nature engineered wood in such a great way to really have cells that will serve different purposes. For softwoods like pine, the most common cell is the longitudinal tracheate, and we can think about it as just having a whole bunch of hollow tubes that go up and down the tree following that longitudinal axis, and they're giving structural support to those cells and to the tree. If we zoom in into that cell wall, then we also have a layer composite. And we have secondary layers as well as primary layers. Each one of those layers is made out of nanofiber reinforced material and has lignin, hemicellulose, and cellulose. Inside the fibril matrix structure, in particular in that S2, which is the biggest of them all, so it really contributes to most of the properties of those cell walls, we have cellulose microfibrils. And these are bundles of smaller elementary fibrils that are made out of cellulose and that are helically embedded along that cell wall, that goes up and down that tree for the S2. So besides all that complexity of structure, it can also absorb water. It has hydroxyl groups, so it likes water, and water can go inside the cell wall, be held there strongly. We call this bound water, or we can also just have free water around that is like present in all those like little spaces, all those cavities that are inside that cellular structure, like the pits and all like those empty spaces inside those hollow tubes. So we quantified the total amount of water that is inside the wood with respect to the weight of the oven dried wood, and we call this moisture content. And the moisture content in wood will change with the environmental conditions. So as we increase humidity, the moisture content, here's the MC, will start going up as well. And then other things will happen as you increase the amount of water in wood, your sample will start changing dimensions. So it would swell most in the tangential direction, followed by the radial, and then just a little bit in the longitudinal axis. And we'll also have like some changes undergoing in the polymer structure inside. So those components that are inside might start changing. They might start experiencing deformations, and the hemicelluloses might start like getting softer as well. And this has been linked to a lot of different myriad phenomena. So it can start decay, faster decay in systems, it can start the corrosion, diffusion of ions through the cell wall, transport, and all these things have been linked to that amount of water inside the wood. So these changes will cause changes in the nanostructure. So how can we study it? Like I've already like went over the structure, and there's like all these differences that happen. So how can we really look at what's happening at the really, really tiny scales? So we can use microscopy techniques, but typically we have contrast problems. So we have a lot of light elements, and it's hard to have good contrast without using some labeling agents. So, and we also have to prepare things very carefully for this technique. So because of that, I use a lot neutron scattering techniques, like small angle neutron scattering. And one of the, they offer many advantages for my research, a few of them being that I can do very minimal sample preparation and be able to slice some samples, conserving the full cellular structure, and be able to see what happens to this different samples as a function of like moisture uptake. I can also use deuterium, which is in this case heavy water. So it still will react like just regular water, but it will have higher contrast in my experiments. And I can also do my own custom built environments so that I can control the humidity inside the chamber where I put my samples. And that way I can start studying in real time what is happening like inside the nanostructure of my system. So what is small angle neutron scattering? So I have here a brief schematic of what my experiment looks like and what type of data I get from it, kind of like real time. So in a small angle neutron scattering, stands for short, we have a neutron beam that is focused onto a sample. And this sample may be inside a titanium cell that is like filled with water, in this case heavy water, to give good contrast, or it may be inside a custom built chamber that allows me to control the humidity inside. And it does this by having a humidity sensor probe that is reading constantly what the humidity inside this enclosure is. And then like I have an inlet and an outlet that just delivers a mix of dry and wet air to get the humidity condition that I'm interested in. And I condition my samples there over a certain period of time, and then I can track how they're changing as the water is going inside the cell walls. Then the neutron goes inside my sample, it interacts with the nuclei inside it, and is then scattered onto a detector. And I like measure the scattered neutrons onto this detector, and this allows me to see directly in residual space what length scales have been changing, and we call that Q. We can probe different length scales simply by changing the sample to detector distance. And typically, if we have really, really long sample to detector distances, we can probe really long structures, like in larger structures. In this case, the packing of those elementary fibrils, which are just like a bundle, and you can think of them like going up helically around the cell. And in this case, they're perpendicular and parallel to that sample, will give rise to this diffraction peak. And then I can simply track that diffraction peak as a function of different conditions to see how the microfibrils are swelling differently based on the modifications I've imparted. So we typically work with Wendy profiles rather than 2D detector patterns, even though they are filled with a lot of information in terms of the alignment. So we typically integrate those 2D profiles, and we obtain a profile that looks like this. It's a 1D dimensional profile, and we can still see like two regimes. In this case, this is for a sample that has been immersed in D2O. So this is how the sample looks like. And we'll have some power law scattering that is scattering from all this super big stuff that is inside my sample and it's not contributing to any correlating distance. But then all the stuff that is really nicely packed, these elementary fibrils that are inside the elementary fibrils, because they're so nicely oriented and packed next to each other, they will give you a diffraction peak, and we can track that diffraction peak, and the diffraction peak is going to be related then to the spacing between this elementary fibrils. In this case, the contrast that we are getting has to do with water going inside those regions between the elementary fibrils. So regions that can see water and regions that cannot will give you that contrast. Using a custom-built humidity chamber, we can track those changes, and that diffraction peak caused by moisture uptake and how like we have more moisture going in to like we eventually get all the way to 95%. We can see how the diffraction peak starts like increasing in intensity, and it can also start changing positions, meaning that those regions between the elementary fibrils are swelling, they're getting larger as more water is going in, and the microfibril is increasing in size. So by tracking that position and the elementary fibril position, we can then know what's the spacing between the elementary fibrils. By obtaining samples from different primary planes, we can then see that the swelling between the elementary fibrils is not primary plane dependent. So like we compare the elementary fibril spacing, we can see that it's all overlapping, which is quite interesting because at the bulk wood level, we see anisotropy in the bulk wood. But the amount of swelling we observe is quite high. It's about 25%, so about 20%, meaning that treatments that are meant to provide durability need to target the swelling, because this is one way to ensure that we have dimensional stable products, right? So are they doing it? Well, let's take a look at what happens when we expose unmodified wood to ground rot. So if we let it sit under in a soil block test and let it be attacked by fungi for 12 weeks, the first thing that happens is that we lose that diffraction peak. So that nanostructure is not protected. And now we don't have like this nice correlation feature between our different elementary fibrils. And if we look at that sample, it's like all crumbly. It's really hard to keep all together. So it's lost all this structural integrity. If we treat it with modification so that the fungal like exposure does not cause weight loss. In other ways, we're protecting that wood so that it's not it's resistant to this brown rot. What happens is that even after those 12 weeks of exposure, and this is like different types of modification, the same type, just different levels, we can see that for all of those types, we still see that diffraction peak, meaning that still preserved. And you look at those samples, they look pretty good. The structural integrity is there. We were able to keep those fibers aligned in our experiments, and that all that like nanostructure has been preserved even after the fungal exposure. If we look at different modification effects, then what we see is that those that were the most resistant, and we are comparing here those empty circles versus filled circles, we can see that all of these ones have still that peak when they're considered resistant, except for those that as you are becoming less and less resistant, so you have some weight loss after you have been exposed to the fungi and you're like becoming crumbly, you're losing some of the material because the decay organisms are eating it away, you can see then that the fraction peak is lost for those. And if we track that position, we also observe that at elementary fibril level, what happens is that there's less water going in. So these modifications are keeping the water out and protecting the nanostructure from, so with that, I've like briefly showed you how we can use science to better understand how to protect wood and what happens to swallowing and what happens when water goes inside the structure. So I will talk a little bit about me, my culture, and where I'm from. So I am from Puerto Rico, La Isla del Encanto. And if you visited Puerto Rico, it's packed with beautiful sceneries and so many things that you can enjoy. And it's a small island, but it's packed with beautiful beaches all around, of course, you expect. And if you visited, you probably visited on the San Juan side. Near that side, there's a tropical rainforest. Near Vieques, which is one of the islands that belong to the main one. We have a bioluminescent bay, and there's two others also like in the island. So if you have never checked out what bioluminescent bay is, this is kind of how it looks like, and pictures really don't do it justice. We have dinoflagellates in the system, and they will glow in the dark in specific conditions. So they're a wonder to behold. And we also have one of the largest underground rivers in the center of the island. So I really enjoy doing ecotourism back home. But I am from the other side of the island. So I'm from the west. Mayaguez is my hometown, and it's like right here. It's about 2.5 hours from San Juan. And if you visit Puerto Rico, chances are you haven't really explored too much of the west side. I think the east side is the more touristy side. We are known for a couple of things. The University of Puerto Rico, which is where the College of Engineering is at. And that's where I got my undergrad from. And also for our mangoes. It's one of the 3 slogans of our city, and they are delicious. We have a mango tree back in my parents' house, and it's the best. We also have, like, very close to our side is Isla de Mona, or Mona's Island, and that's about like 3-hour boat ride away. And you need to be experienced because you would need to cross the Puerto Rico Trench, which is like a really deep trench in the Atlantic, and it's a beautiful natural reserve. So it's hard to, I believe, like visit, but if you get a chance, I think it totally would be worth it. And I'm planning on making a visit in the nearby future. I have a fun fact about like differences among the island. So despite the small size, we have some variations of what we call a few things. So one of the things that, especially in the West, is that depending on what you want, if you're trying to get a pastry, you really need to be specific and explain the filling that you're interested in. And I have some pictures here. So if you ever visit, you know what you want, what you're ordering. So for instance, this is an empanadilla for us. And I think in some places here, they call them empanadas. They're fried. They typically have like a savory filling. But then like we also have pastelillos. And then pastelillos are typically baked. And they have like this puff pastry, and they can be savory or sweet. But if you go up to some areas in the West, like near Aguadilla, for instance, you could accidentally end up with the other version of this if you are not specific about what your filling is, because in some places in the island, they'll call empanadillas pastelillos, or pastelillos empanadillas, and vice versa. So it's always kind of a fun fact to make sure that if you want to order one of these at a place, you kind of need to be specific which one you want. My favorite time to visit is Christmas. It is beautiful, especially coming now from the frozen tundra, aka Madison, Wisconsin. It means that I get to have beautiful weather. It's like 70 degrees during Christmas season, and we also have a very, very long Christmas season. People start decorating right after Thanksgiving, and decorations are usually up all the way to like mid-January after what we call las octavitas, which are like about 8 days after the Epiphany. So after January 6th, we still have like parties and like decorations and different things like all throughout the different cities 8 days after January 6th. Also, January 6th is a holiday in Puerto Rico, so I really like as much as possible to try to be there during that time. And I have pictures here of the La Plaza, which is like the center of the city, is decorated during Christmas. You can see a lot of nativity scenes around. And then on January 6th, you see the three wise men usually will go in horses, and like this happens in all throughout like neighborhoods. They have festivals too, but usually like people will go dressed as the three wise men, and will like throw candy or like bring gifts to the kids on the 6th. So it's probably one of my most favorite things ever. That I think I'm ready for questions.